Chapter 6: Errors, Error Detection, and Error Control. After reading this chapter, you should be able to 1. Identify the different types of noise commonly found in computer networks. Specify the different error prevention techniques and be able to apply one to a type of noise. Compare the different error detection techniques in terms of efficiency and efficacy. Perform simple party and longitudinal party calculations and enumerate their strengths and weaknesses. The next step is, or the next objective of this chapter is, cite the advantages of cyclic redundancy checksum, CRC, and specify what types of errors it will detect. The next objective is, cite the advantages of arithmetic checksum and specify what types of applications use it. Differentiate between the basic forms of error control and describe the circumstances under which each may be used. And the final objective, follow an example of humming self-correcting code. We are just skimming, so we are not gonna read every single word in this chapter. We'll go through the key terms and we'll see what can we cover here. So if we scroll down, we will reach the noise and errors. And what is the white noise? It's called thermal noise or Gaussian noise. Is a relatively continuous type of noise and is much like the static you hear when a radio is being tuned between two stations. It's not really hard to remove. It's a white noise. So basically in programming, they use the term white spaces for the harmless spaces, and in telecommunication they use the white noise for the harmless noise. So it's basically they use the word white like harmless or something like that. So this is a white noise in the figure here, and this is much noise. It's not little noise, but still white noise. It won't change the 0 to 1 or the 1 to 0. You still get the main square wave on the figure A on the top. So if we continue scrolling down, we have the impulse noise, or they call it a spike, just like a sudden change, upward or downward. It's a spike, okay? A non-continuous noise, and one of the most difficult errors. It's really difficult to detect because it occurs randomly. Pay attention to the word randomly. It's not expected. The effect of impulse noise on digital signal. So it changes. This is just a white noise until here, then here it changes. The impulse changes the 0 to 1 and the 1 to 0 and make a big problem. Transmission speed and its relationship to noise in digital signal. So the higher the speed, the more difficult. That's really basically it. We see the slower speed, the noise is not really going to change much. But when it's fast speed, the noise is going to influence many bits. All right. Crosstalk. Crosstalk is unwanted coupling between two different signal paths. So they just like combine. They crosstalk. It can be electrical, might occur between two sets of twisted pairs, or it can be electromagnetic crosstalk, or it can be at any level, logical level or something. The 3 phone circuits experiencing crosstalk. So all these experience crosstalk. Echo is just the echo that we know. Is the reflective feedback of a transmitted signal as the signal moves through medium. And this happens with microwave and with many other types, the echo. And there are so many echo cancellation ideas. The modulation can reduce echo. The use modulation technique can reduce echo. So the echo is a signal bouncing back at the end of the coaxial cable and causing echo. It reaches all the way here to the end at the right side. Then that dotted blue is the echo. Jitter. What is the jitter? It's the result of a small timing irregularities that become magnified during the transmission of digital signals as the signal are passed from one device to another. So it's delays, jitter, delays in a proper timing, in proper synchronization. And this is a jitter here. That on the top we have the original square wave, and digital signal with jitter, you can see the delays somewhere here and here and here. Attenuation, or it's getting weaker. It's a continuous loss of signal strength as it travels through medium. All right, error prevention. How to prevent errors. You may prevent the occurrence of many types of transmission errors by applying proper error prevention techniques, including those listed here. What are the techniques? Install wiring with the proper shielding. Put a shield. Use shielded twisted pair, not unshielded. Use shielded coaxial cable. Use shielded fiber optics to reduce electromagnetic interference and crosstalk. Be aware that many different types of wireless applications share the same wireless frequencies. Even some non-wireless devices generate signals that can interfere with wireless applications. For example, microwave ovens can interfere with some wireless LAN signals. All right, replace older equipment with more modern digital equipment. Although initially expensive, this technique is often the most cost-effective way to minimize transmission errors in the long run. So update your devices. Use the proper number of digital repeaters and analog amplifiers to increase signal strength, thus decreasing the probability of errors. If your strength is strong, if your signal strength is high, then the noise ratio is relatively small. If your signal strength is low, closer to the noise, then your noise to signal ratio is high. The next point to prevent errors is observe the stated capacities of the medium and to reduce the possibility of errors. Avoid pushing transmission speed beyond their recommended limits. Avoid reaching the limits. And all, like switch limit, transmission media limit, everything, like in all levels, at all levels, in all dimensions. Summary of error and error prevention techniques: white noise, impulse noise, crosstalk, echo, jitter, and attenuation. And here's the error prevention: to reduce the white noise, to reduce the impulse, to reduce crosstalk, to reduce echo, to reduce jitter, to reduce attenuation. This table is really important. I recommend reading every single word of this. But we are skimming to save time and to avoid make you really bored. We'll keep going. Error detection. We talked about the errors. We talked about how to prevent them. Now we are going to talk about how to detect them. And if we keep going, we have the parity checks. It's the most basic. error detection technique, which are commonly used with asynchronous connections. And we talked about the party checks. So basically, party checks let too many errors slip through undetected. So it has single character party check and one fact remain. Party checks let too many errors slip through undetected. So party check is rarely used. It's not efficient. Simple party, even or odd party check. It's a bit that if the number of zeros is even and it's an even party, then it became 0. If the number of number of ones are odd and it's an even party, then it turns 1. And this way you know if there's something changed in that data. Longitudinal party, sometimes called longitudinal redundancy check, or horizontal party, tries to solve the main weakness of simple party, that all even numbers of errors are not detected. To provide this extra level of protection, longitudinal party needs to use additional party check bits, as you will see shortly. So here's a simple example of longitudinal. Row 1, row 2, row 3, row 4, and party row. So this is the party row. If it's even, it's 0. If it's odd, it adds 1 to make it even. This is a simple example of longitudinal party. The second and third bits in row 1 and 2 have errors. The same example. This second bit became 0. The next one became 1. And same with here. 0. So all these get problems. The result is the same. So it's not really. But longitudinal party does not detect the errors. So it didn't really detect them. This is a weakness. All right. Arithmetic checksum. Many higher level protocols, see the word higher level, it means it's not at the level of zeros and ones, but at the higher level, a level of a group of bytes that usually 4 bytes form an integer. All right. So many higher level protocols use on the internet, such as TCP/IP, use a form of error detection in which characters to be transmitted are summed together. This sum is then added to the end of the message, and the message is transmitted to the receiving end. So it adds the summation. The receiver accepts, and that's used in the TCP/IP protocol. The receiver accepts the transmitted message and performs the same summing operation and essentially compares its sum with the sum that's generated by the transmitter. If the two sums agree, then no error occurred during transmission. If the two sum does not agree, the receiver informs the transmitter that an error occurred, and maybe it will ask it to resend it because the sum is generated by performing relatively simple arithmetic. This technique is called arithmetic checksum. So it's by sending the sum, and the receiver is going to calculate the sum and compare it with the sent sum. This is the basic idea. If we add this column values, you will get this. The sum as this. It's added to the outgoing message. All right. And for details, we can read this. And in the hexadecimal arithmetic system, we use from 0 to 9, from A to F, because it's 16 digits. So we see A and D and B and E and C. Yeah. So this is partial sum, and this is final carry, and this is the sum. CRC, or cyclic redundancy checksum. Unlike the simple party and longitudinal party techniques of error detection, which produce high ratios of check bits to the data bits with only micro error detection results, the CRC, or cyclic checksum method, typically adds 8 to 32 check bits to potentially large data packets and yields an error detection capability approaching 100% checksum. All right. The CRC error detection method. So this is for detecting errors. Okay. Treats the packet of the data to be transmitted as a large polynomial. The far right bit of the data becomes the x to the power of 0, and the next to the left is x to the power of 1 term, and so on, x to the power of 2, x to the power of 3, x to the power of 4, just like that. When a bit in the message is 1, the corresponding to polynomial term is included. Thus, the data 1, 0, 1, 0, 0, 1, 1, 0, 1 would be equivalent to the polynomial 1, and just like it gives a weight. It gives a weight. So this is 1 plus x to the power of 0, and 0 plus x to the power, but it's 0, so it's to the power of 1, and this is power 2, and this is 3, and this is 4, 5, 6, 7, 8. So this is the power of 8. The right hand is the least significant, just like normal numbers. The left hand is the high significant. When you write a million, the one at the right has a big weight, right? Just like normal mathematics. Because any value raised to the 0th power is 1, and x to the third terms is always written as 1, the transmitter takes this message polynomial, and using polynomial arithmetic divide it by a given generated polynomial and produce a quotient and remainder. The quotient is disregarded, but the remainder in bit form is appended to the end of the original message polynomial. So it considers the remainder of the division. This combined unit is transmitted over a medium. When the data pulse remainder arrives at the destination, the same generating polynomial is used to detect an error. A generating polynomial is an industry-approved bit string used to create a cyclic checksum remainder. Some common generating polynomials in widespread use include CRC12, just like that, CRC16, CRC-CCITT, CRC32, asynchronous transfer mode. The receiver divides the incoming data, the original message, polynomial plus the remainder, by the exact same generating polynomial used by the transmitter. If no errors were introduced during the transmission, the division should produce a remainder of 0. If an error was introduced during the transmission, the arriving signal message polynomial plus the remainder will not divide evenly by the generating polynomial and will produce non-zero remainder. Signaling and error detection. If the remainder is non-zero, is 1, then there is an error. In real life, the transmitter and receiver do not perform polynomial division with software. Instead, hardware design into an integrated circuit can perform the calculation much more quickly. It's just a logical circuit. CRC method is almost foolproof. Table 6.4 summarizes the performance of the CRC technique. Let's go to the table right away. Error detection, performance of CRC or cyclic redundancy checksum. Single bit error 100%, double bit errors 100%, odd numbers of bits and errors 100%, an error burst of length r plus 1 100%, an error burst of length equals to, that's less than r plus 1, this is equals to r plus 1, there's a probability which is very near to 100%. An error burst of length r greater than r plus 1, probability is very near to 100%. So it's really the CRC checksum calculations. And here is a hardware shift register used for CRC generation. So we have an exclusive OR. This is the incoming data. One bit goes here, a second bit, a third bit, a fourth, a fifth, and XOR, and yeah. Example of CRC generation using shift register method, which is this one, I guess. This is a shift register. Hardware performs process of polynomial division very quickly. Basic hardware used perform calculation. A simple register that shifts all data bits in the left every time and no bit is entered. So just keep pushing it from the right to the left. And this is called shift register. Example of CRC generation using shift register method. And if we keep going, this is error control. Okay, we are done with the error detection. We talked about simple methods commonly used. We talked about the CRC. We talked about the arithmetic. Let's go back. Arithmetic checksum, and we talked about the party checks, which is simple and longitudinal. Now we'll go back to the next section. Now we are done with the error detection briefly, so very quick skim. Now we are going to the error control. That's error correction. Now, if you recall, we just talked about detecting the error. Just detecting. All right? Once an error in the received data stream is detected, what is the receiver going to do about it? Either correcting or re-ask for retransmission. The action that receiver takes called error control, which essentially involves taking one of three actions. Toss the frame packet, return a message to a transmitter asking to resend the packet, that was an error, or correct the error without retransmission. It's either recorrected or ask for resend or just ignore it. If you have a live stream, there's no point of retransmitting because the detected error, you just ignore it and keep going and display the next and the next and the next frame, just a live stream. If it's not a live stream, then you can either re-ask the send, but it would be nice to save the bandwidth and the round trip and just correct it from yourself. So this is the really hardest. This is the medium. and this is the very easy choice. So we have three options, one of three options. The toss frame packet is the first error control. Tossing the frame packet hardly seemed like an option at all. Yet tossing the frame for error control is becoming a mode of operation for some newer wide area transmission techniques. And if we keep going, you can see that. Toss the frame. Okay. Return a message. So stop and wait error control. Over years, two basic versions of return a message error control have emerged. Two basic ones. The first one is stop and wait, and the second one is sliding window. Stop and wait. So you just, okay, resend it to me. You stop and wait. And there is a timeout. All right. So here is the data. Here is the acknowledge, data sent, not acknowledge, data resent. Just like that. If data arrived without errors, you acknowledge receiving. If data arrived with errors, you ask to resend. Simple dialogue using stop and wait error control. This is the very basic one. Sliding window error control. Sliding window error control is based on the sliding window protocol, which is a flow control scheme that allows station to transmit a number of data packets at one time before receiving some form of acknowledgement. So they keep sending, then they get the acknowledgement. Sliding window protocol have been around since the 70s, a time when computer networks had two important limitations. All right. So here we have the 0, 1, and 2, and data arrived without errors. Acknowledge the 0, 1, and 2. If something happened, it will let the sender know, and the receiver will rearrange the packets. All right. So they can acknowledge from 0 to 100, from 101 to 800, acknowledge both in one. All right. And if we keep going, three examples of returning an acknowledgement in TCP/IP. So from 201 to 350, and acknowledge 351, 351 to 500, then 501 to 700, and here acknowledges 701. So instead of keep acknowledging every thing they receive, they acknowledge the very final result. That means we received everything before that. Lost packet and station B's response. Something get lost here. So they just acknowledge whatever they received. Anything after the lost, they don't acknowledge. And they just send the missing, and they acknowledge the very final thing. So they don't really disregard the third one. The first one received, the second one missing, the third one received, they just acknowledge the receiving of the first, the second gets sent again, they acknowledge the whole three. So this is called held in buffer. It stays in a storage, temporary storage, at the receiver end. Lost acknowledgement and retransmission of a packet. If the acknowledgement did not show up, then the sender keeps sending it until he gets an acknowledgement. All right. Correct the error. Now we would like to correct the error. We talked about three options, 1 or 2 or 3 at the very beginning here, which is either tossing the received, where is it? So basically it's either tossing the received signal or asking for the retransmission or correcting. So we talked about the first and second, now we are going to talk about correcting the error. The beginning of this section on error control listed three actions a receiver can take: toss the frame packet, return an error message, or correct the error. Correcting error seems like a reasonable solution, and it's the most sophisticated. Of course, if you have the ability to correct error, that's perfect, right? All right. Unfortunately, correcting an error is not that simple. For a receiver to be able to fix an error in a process called forward error correction, redundant information must be present so that the receiver knows which bit or bits in an error or what their original values were. For example, if you were given the data this and informed that party check had detected an error, would you determine which bit or bits were corrupted? No, you would not have enough information. A more useful type of forward error correction is Hamming code. Hamming code is a specially designed code in which special check bits have been added to the data bits that if an error occurs during transmission, the receiver might be able to correct the error using the included check and data bits. All right, so we have Hamming code. Generate check bits generated from the data. So we have the data and Hamming code added to it for error correction. So you are adding more information. All right. And here's an explanation of the Hamming code. All right. Details: forward error correction, and Hamming distance. Hamming distance. The Hamming distance is a character of a code. To create self-correcting or forward-correcting error correcting code, you must create a code that has the appropriate Hamming distance. All right. Error detection in action. Error detection in action. It rhymes. You are working for a finance company, and here is a scenario with an error correction, and we'll just leave that. And here's the chapter summary that talks about everything we just covered, or we just really skimmed really quickly. And this is the completion of the summary. Here's the key terms, the review questions, interesting exercises. All right. And the thinking out of the box exercises, which is really useful. And to avoid making this recording really long, I'm not going through every single word here. And hands-on projects using the programming language of your choice, for example, C++. Write a program that inputs a character string, All right, you take a string and calculate the Crc checksum remainder using a given generated polynomial. And you get from the ASCII, you get the ASCII code for every single character of the string. Then you go through the checksum, cyclic checksum remainder. Start shifting. This is really interesting program. All right. And next we'll talk about chapter 7, LANs, part 1. Then chapter 8 will be local area networks. Part 2